Hi, my name is Stephen. I'm going to be introducing the topic of in-memory processing. Mostly that'll be through the use of a survey paper, but I'll also provide some background information that's needed to fully understand it. The survey paper is called Enabling the Adoption of Processing in Memory, Challenges, Mechanisms, and Future Research Directions. The authors use a term PIM, P-I-M, processing in memory. And that just means performing operations on the data in the DRAM, in the main memory, instead of in the processor where it's normally done. They also use a term NDP, near data processing, to refer to the same thing, but PIM is the acronym that they use most. So why do operations on data in memory? Why not just use the processor like normal? Well, there's a few reasons for that. For one thing, DRAM latency has become the main bottleneck in many systems. And that happens for a couple of reasons. For one thing, innovation in DRAM has lagged behind that of processors. Also, there is an increase in the working set sizes. There's simply more data that's needed to solve current problems. If the processor is going to do the operation, the data must be moved to and from the memory in the processor. The process of moving the data back and forth between the main memory and the processor can actually be slower than the computation itself. The bottleneck between the system memory and the processor is both in terms of performance and in energy consumption. Depending on the problem being solved, the processor may not even be able to reuse the data, so it doesn't even make sense to bring it into the cache. The good news is some operations are actually well suited to in-memory processing. Some operations don't really take advantage of cache anyway, and we'll go into some more detail on that later in the presentation. The other good news is that it's already possible with many forms of DRAM to perform in-memory operations. In particular, modern 3D DRAM includes very high internal bandwidth, and oftentimes there's even an internal logic layer included in the DRAM, which we can use, and we'll go into more detail on that later as well. Making use of this logic layer will be the main focus of the techniques presented in this survey paper. The two techniques presented in this paper, in-mem-proc and lazy PIM, attempt to address some of the limitations that exist with PIM. One of those limitations is the fact that the DRAM doesn't have good access to some features of the CPU that are essential, such as virtual memory, the translation look-aside buffer, or the page table walker. And that's one thing that in-mem-proc attempts to address. The other limitation is that of cache coherence mechanisms. We need to maintain coherence between the main memory and the processor cache, but not at the expense of frequent communication between the two. We're trying to minimize that as much as possible. So that's where lazy PIM comes in. So in-mem-proc is an in-memory accelerator to let us quickly traverse a chain of virtual memory pointers within the DRAM without having to take advantage of the CPU. And one of the things that makes this possible is the fact that there is very high bandwidth in modern 3D stacked DRAM. And the other method that we're going to discuss, lazy PIM, is a way to maintain cache coherence in a lazy way that tries to minimize the back and forth communication with the CPU. It works in a speculative way, so it assumes that cache is coherent and it queues up requests and then does them in batches to minimize back and forth communication with the CPU. So next I'll talk about how DRAM works, and then I'll talk about how to use PIM in an application. DRAM is dynamic random access memory, and this is the predominant technology used to build main memory in systems today. In these diagrams, you can see how DRAM is organized in a hierarchical fashion. The highest level is the module. This is the level at which the processor's memory controller interacts. The memory channel between the memory controller and the DRAM is 64 bits, which is then further subdivided into 8-bit buses, one for each of the 8 chips in the module. Each chip in turn is divided into 8 banks and also includes some peripheral logic and the I/O interface. Each bank is then subdivided into subarrays, subarrays consisting of mats, and there's a row decoder for selecting which subarray, and global sense amplifiers that move data on the global bit lines. Finally, within each mat, we can see an array of 512 by 512 data cells, each one representing 1 bit, connected together by word lines and bit lines, and controlled by the word line drivers and the local sense amplifiers. Zooming in a little closer, you can see how the memory cell connects within each mat. The memory cell consists of a capacitor, which holds a charge, and a transistor to connect it or disconnect it from the bit line. The sense amplifier for each bit line consists of 2 logical inverters connected back to back in such a way that they want to reach a steady state of either 0 or 1. When the memory controller issues a pre-charge command, they are actually exposed to a 50% charge. So it's neither a 0 or 1. But then when they are connected to one memory cell, they get pushed either to a 0 or a 1 and latch onto that value. The act of reading the memory cell, though, depletes the memory cell's capacitor. So the value stored in the sense amplifier is then used to recharge the memory cell. This standard DRAM implementation has been used in the past to implement older in-memory processing techniques. For example, if the pre-charge command is not issued, then you can expose the sense amplifiers to multiple rows in succession, which causes it to act like a majority vote. So by connecting together several rows with all zeros or all ones, you can create bitwise and or operators for an entire row. Of course, that depends on if your DRAM allows you to activate more than one row without calling the pre-charge first. The DRAM shown before was standard 2D DRAM, but we're going to be looking at 3D stacked DRAM, which gives us a couple of interesting features. Multiple layers are stacked on top of each other and connected by way of TSVs, or through silicon vias, which are very high bandwidth connectors. In fact, the bandwidth is much greater than that which connects to the CPU. The other interesting feature is that there is often incorporated a logic layer which we can use to perform simple operations on the data in the DRAM itself without the help of the CPU. 2 examples of this architecture are HBM, high bandwidth memory, and the hybrid memory cube, HMC. Even in DRAMs where there is a logic layer, it is often underutilized, and so there are several proposals out there to make better use of it. While there is currently no one standard interface between the PIM logic and the CPU, the basic idea is that the CPU delegates certain commands to be run in the DRAM logic, like a coprocessor. And these little blocks of code are called PIM kernels. Although implementations do vary, it is common to expect the compiler or programmer to specify which code should be offloaded to be executed by the PIM core. So for example, in your high-level programming language, you could have a macro that defines which code block should be executed as a PIM kernel. There are two key issues when making use of PIM. The first is address translation, and the second is cache coherence. One naive solution for either of these would be to just have the PIM architecture say that it doesn't support it. So it could just make it clear to programmers that it doesn't support address translation, or it can't guarantee cache coherence. The problem is that this alters the programming model of the system, and so it makes it harder for programmers to write software for it, and it makes it less likely that that architecture will ever get adopted. Address translation is something that code often relies very heavily on, and this is the process of taking a virtual memory address, such as what's stored in a pointer, and translating that into a physical memory address. So this gets used a lot when traversing complex data structures. Cache coherence is an issue that arises because the PIM logic is able to write to the data and make changes, and at the same time you might have multiple cores of the CPU reading and writing data that's in the cache, and so these things all need to remain in sync with each other and coherent. Although it may be unrealistic to expect the PIM architecture to maintain a very fine-grained coherence like the processor, still, if the PIM architecture can maintain some coherence, it makes it easier for a programmer to develop software, and also it makes the architecture more likely to be adopted. Both of these problems are already solved in the CPU with existing structures, but we don't want to keep using the memory channel to access them, which would defeat the whole purpose of trying to minimize usage of the memory channel. That's why this paper makes the case for the two techniques, in-mem-proc and lazy PIM. So the first technique that this paper discusses is in-mem-proc, and that's short for in-memory pointer chasing accelerator. When developing in-mem-proc, there are two main challenges. The first is parallelism, and the second is the virtual to physical address translation without the CPU's help. Parallelism is difficult to achieve even in the high bandwidth environment of 3D stacked memory, and the reason is because of dependent sequential accesses. Whereas a multi-core CPU can handle multiple concurrent streams of link traversal, this is much more difficult to do in a simple accelerator. It turns out that the main bottleneck in this accelerator is the memory access latency, and that the time it takes to compute the addresses for link traversal is actually only a small part of the time needed. And so the accelerator would sit idle for a majority of its time. So what in-mem-proc does is to decouple the link address generation from the issuing and servicing of a memory request. This allows it to concurrently wait on one stream while it begins another one. This kind of address access decoupling is actually a specialized form of a decoupled access execute architecture, which has been used in other contexts. The second challenge is address translation. An accelerator must be able to turn a virtual memory address into a physical address. Using the CPU's TLB or page walker to solve this, or trying to duplicate that in the DRAM, are impractical. But what in-mem-proc does do is limit the link traversal to linked data structures and keeps the data structures in a contiguous section of virtual memory, and relies on a page table that is region-based. To motivate the need for a pointer chasing accelerator, we can look at all of the different cases where there is serial traversal of links. This includes linked lists, file systems, routing tables, hash tables, B or B plus trees, to name a few. These data structures allow nodes to be inserted, removed, moved with ease. But as ubiquitous as they are, the node traversal is actually pretty inefficient with just the CPU. And the reason is because at every step, another memory access has to be made. It's also unlikely that cache will be able to help out, and there will be a lot of misses. To help quantify the impact of these link traversals, two applications were profiled. The first being memcached, which is an in-memory caching system using a real data set from Twitter. And the second one is DBX1000, which is an in-memory database system. In the first chart, you can see that pointer chasing accounts for a small but yet significant portion of the execution time. But in the other two charts, you can see that the cycles per instruction and the amount of cache misses is largely accounted for by the pointer chasing and not from the rest of the application. There have been some prior works that attempt to hide the memory latency by using prefetching. Although prefetching for a data structure can help a little, there are also some downside risks that can be significant. For example, if multiple paths are traversed, and often these prefetchers have to be designed for specific data structure implementations, and so they don't work well in the general case. The trick in-mem-proc uses is to do all the traversal in memory and only return a node to the CPU once it reaches the final node. So the logic layer of the DRAM is doing all the work, and we're not using the memory channel until the very end of the search. This offers three big improvements. First, obviously there's time saved by not making all of the round trips with the CPU. Plus, it frees up the CPU to work on other tasks. And also, it reduces use of the cache, which saves time wasted from contention. To accomplish this, and to ensure some degree of parallelism, the in-mem-proc architecture has two main parts. First, an address engine, which generates the addresses specified by the pointer, and secondly, an access engine, which performs memory access operations using addresses generated by the address engine. The architecture is very simple from the CPU's point of view, and it doesn't require any special knowledge from the programmer. First, the CPU puts a request in the request queue. Then the address engine services that request out of the queue by loading the pointer chasing code from the instruction RAM. Whenever the address engine encounters a memory instruction, it enqueues the address in the access queue and then performs a context switch to begin working on a different stream. That way it can continue working during the relatively long memory access operation. When the response is returned from memory, it is then put in the response queue, and the address engine monitors that queue, so when the response comes in, it knows to return to execution in the pointer chasing algorithm. in-memory also uses a cache specially tailored to pointer chasing applications. It uses cache line locking to ensure that the data will be there in the cache until the operation is finished. And items are immediately evicted from cache when they're no longer needed for that operation. To minimize communication overhead with the CPU, requests and responses are handled in the form of packets written directly into the memory. The following pseudocode of a B-tree search method demonstrates what it would look like to a programmer. On the left is the conventional way of searching the tree to find the node. And on the right, there are just a couple of small changes when using in-memory. First, instead of the parameters being passed in directly, they're accessed by the __param API, which ensures that the program explicitly reads the parameters from the predefined memory map locations of the data RAM. And at the end, instead of the usual return statement, again, the param API is used to place the result into memory. Here are some other design considerations that went into in-memory. in-memory uses a region-based page table, which is optimized for in-memory pointer chasing. It's organized into 3 levels. The first level is a region table, which needs to map only a small number of the contiguously allocated in-memory regions. And then a second level flat page table for each region, about 2 megabytes each for page size. And then finally a more traditional page table with 4 kilobyte page size. This design minimizes the number of misses during link traversal. Additionally, the size of the in-memory regions are configurable so they can be tuned to the particular application. The API ensures that memory is always allocated in contiguous regions. Maintaining cache coherence between the CPU and the in-memory caches is also an important factor. This is accomplished by enforcing that any code that operates on the in-memory regions must be executed in the in-memory accelerator. More complex strategies could also be employed, such as what we will talk about with lazy PIM later in the presentation. If a system is going to use memory stacking because more RAM is needed, then the performance of in-memory could be significantly impaired. And that's because it would have to go through off-chip memory access channels, which would negate the benefits of using in-memory in the first place. But to get around this, the authors suggest that the operating system be modified in such a way that all in-memory regions are allocated in the same memory stack, and the same for the in-memory page tables. And this ensures that the highest bandwidth connections are used. So now to evaluate how well in-memory works, here is the methodology that was used. They started with the GEM 5 full system simulator with the DRAM Sim 2, and they chose the 64-bit ARM version 8 architecture. 4 cores at 2 GHz, 64-bit Linux, 32 kilobyte level 1 cache, 1 megabyte level 2 cache, DDR3 1600 main memory, and the in-memory accelerator is set at 500 megahertz, 32 kilobytes cache, and 16 kilobytes data RAM, and 16 kilobytes instruction RAM. There are 4 kinds of workloads used for evaluation: linked lists, hash tables, B trees, and then a DBX 1000 database. For the linked lists, a health-related data set was used and was measured over 30,000 iterations of linked list traversal. For the hash table, the in-mem-cached implementation was used with the insertion of 2 to the 20th random keys into the hash table with 2 to the 20th buckets. And the evaluation was run for 100,000 random key lookups. For a B tree, they used an implementation of DBX1000 using a 16-way B tree with 64-bit integers as the keys of each node. They randomly generated 3 million keys, inserted them into the tree, and then measured the performance with 100,000 random keys. And finally, they used a different DBX1000 implementation with the TPC-C benchmark. This included tables with 2,000 customers and 100,000 items. And after a brief warm-up period of 2,000 transactions, they measured the performance for the next 5,000 transactions per thread, and there were 4 threads. The evaluation was run 3 different ways. Once with the baseline configuration, then the baseline with an extra 128 kilobytes of level 2 cache added, which would be the equivalent of in-mem-proc, and finally running it with in-mem-proc. The evaluation showed that adding the additional level 2 cache made very little difference, about 0.02x speed up. Whereas for adding in-mem-proc, there was a 1.92x speed up for linked lists, 1.29x speed up for hash tables, and 1.18x speed up for the B tree. To get a little more insight into this, they also looked at 3 other measurements. First, the total TLB misses, and found that in-mem-proc reduced the number of TLB misses by about half. They also looked at normalized cache miss latency and found a slight reduction. And they also looked at memory bandwidth usage in terms of gigabits per second and found that the DRAM was being utilized more with in-mem-proc, as expected. For the DBX1000 database test, they used 2 slightly different metrics. First is normalized throughput. They found that adding the extra 128 kilobytes of level 2 cache, again, only made a very small contribution to throughput. Adding an extra 1 megabyte of level 2 cache yielded about a 5% increase in throughput, but running in-mem-proc yielded about a 16% increase in throughput. One interesting thing about this is that because the DBX1000 spends about 19% of its time on pointer chasing, seeing a 16% overall improvement in throughput is very close to the upper bound of what you can do with an accelerator here. And the other metric is normalized latency. And they found that the small amount of level 2 cache made very little difference. The extra 1 megabyte of level 2 cache made a good difference, but again, in-mem-proc showed the best decrease in latency, which was about a 13% reduction. They also ran some tests using different TLB sizes and page table designs, but found that it had a negligible impact on performance for in-mem-proc. And they also looked at energy efficiency and found that even though the power needed increased using in-mem-proc by 5.6%, the execution time was shorter, and so overall the total amount of energy needed to be consumed was reduced by 10 to 40%, depending on which data structure type. So in summary, in-mem-proc provides an efficient way to do pointer chasing in memory. So now I'll describe the other in-memory processing technique called lazy PIM. Lazy PIM is an efficient cache coherence mechanism for processing in memory. Because when working with PIM, we're trying to reduce the amount of memory channel usage, one approach would be to simply sidestep the coherence issue and just restrict PIM to execute on non-cacheable data, or to force processor cores to flush or not access any data that could potentially be used by PIM. In fact, the in-mem-proc method that we discussed earlier sidesteps the issue in this way. In that case, the algorithm was able to function well using its own section of memory, and so coherence was less of an issue. But for the general case, lazy PIM provides better cache coherence when doing processing in memory. Lazy PIM was designed so that it can behave like a traditional cache coherence model, but still retain all the benefits of PIM. In a nutshell, lazy PIM speculatively assumes that it has coherence and then batches up requests and sends them all at one time, and deals with rolling back changes later. So why do we need to worry about cache coherence between PIM and the CPU? Some parts of a program are better suited running on the CPU, and some better suited to run in memory, depending on how they exhibit locality. And we'll need to assume that there will be a lot of data sharing between the two, as demonstrated by many modern applications. Ideally, we could maintain coherence at a very fine-grained level, such as with MESI, but that's unrealistic for PIM applications because it would require sending a lot of messages back and forth, which we're trying to avoid. And if we use cache poorly, then it'll offset the gains of using PIM in the first place. The authors examined the impact of 4 different cache coherence approaches on PIM. The first is CPU only, a baseline where PIM is disabled. Secondly, a fine-grained coherence, which is like the MESI protocol, which is common in many modern systems. Third, a coarse-grained lock-based coherence, where PIM cores gain exclusive access to all PIM data during the PIM kernel execution. And finally, non-cacheable, where the PIM data is not cacheable in the CPU. Also, for the purpose of comparison, they include an ideal PIM scenario where there's no penalty at all for cache coherence. This chart shows how those different approaches perform under different workloads. Coarse-grained seems like a reasonable alternative to fine-grained, but unfortunately it can still lead to high overhead. Some applications can actually perform much worse. Also, with coarse-grained, sometimes data will end up ping-ponging between the processor and the PIM cores. The solution to that is to add locks, but then the locks have their own way of degrading performance, and they can cause thread serialization in a multi-threaded environment. So although coarse-grained may work in some edge cases, it's not good in the general case. The non-cacheable option is a way to sidestep coherence by marking the PIM data region as non-cacheable in the processor. As long as the data is accessed by the PIM core and rarely by the CPU, this incurs little penalty. But with many applications, there is enough data being shared that it's like turning cache off completely. So the performance overhead is too great. So in summary, there is a need for a more efficient cache coherence model for PIM that gets as close to the ideal as possible, even across many different workload types. That's where the lazy PIM proposal comes in. When they access memory, they speculatively assume that they have the required permissions for coherence without actually sending messages to the main processor over the memory channel. At the end of the execution of a PIM kernel, it sends a list of memory addresses where it may have read from or written to. And then the memory manager in the main processor checks to see if there were any conflicts with those addresses. If there were conflicts, the changes are rolled back and the kernel executes all over again. But if there were no conflicts, then the changes become permanent and execution can continue as normal. To minimize changes to the processor design, when using LazyPim, the processor executes non-speculatively. So this scheme produces much less coherence traffic than a traditional fine-grained model. This approach also works well with multiple concurrent processor threads and PIM kernels because it lacks the frequent coherence requests that may cause ping-ponging between the PIM cores and the processor. It's important to note that LazyPim provides coarse-grained atomicity, which means that all PIM memory updates are treated as if they all occurred at the same moment that a PIM kernel finishes execution. So that means for every cache line read by a PIM, if a CPU modifies that line before the coherence check occurs, then the PIM would unknowingly use stale data, which would be incorrect. In this diagram, time flows from top to bottom, and it demonstrates an example of this. In step 1, CPU 0 writes to line C during kernel execution. In step 2, CPU 0 writes to line A before kernel execution, which was not written back to DRAM. To detect such a conflict, it records the addresses of the processor writes and the PIM kernel reads into two different signatures, and then check to see if there's any matches between the two, which would indicate a conflict. If the PIM kernel writes to a cache line that is later read by the processor before the kernel finishes, this is not a conflict. An example of that is the second write by the PIM 0 to line B. Any read by the processor during PIM execution is ordered before the PIM kernel's write. The processor can't read the PIM kernel's writes because they're marked by the kernel as being speculative until the kernel finishes. Here is a simple C program to demonstrate the programming model. It's designed to be simple for the programmer, using two macros, pim begin and pim end, to specify which code should execute in the PIM core. You also need to specify which allocated data will be accessed by the PIM cores. And this is done with the annotation @pim before each declaration. This should include any data passed by value, such as the parameter GA on line 1. And the compiler will handle all of the other details when it translates this into machine language. When an application reaches a PIM kernel trigger instruction, the processor dispatches the kernel's starting program counter to a free PIM core. The PIM core makes a checkpoint and then begins executing the kernel. The PIM core cache has a 1-bit flag on each line to mark it as being speculative if it's accessed. If one of those lines is selected for eviction, then the core rolls back to the starting program counter and discards the updates. During PIM kernel execution, 3 sets of addresses are stored. First, the CPU write set, which is all CPU writes to the PIM data region. Secondly, the PIM read set, which is all PIM reads. And third is the PIM write set, which is all PIM writes. These are then used at the end of the kernel execution to determine if there was a conflict. To reduce traffic on the memory channel, when these lists are transmitted, they are actually quickly hashed into a single fixed length register. This hashing means that there may be some limited number of false positives, but there is an upper bound on the amount, and it's worth the trade-off. For detecting conflicts, the PIM read set and PIM write set are sent to the processor. If there's no overlap between the two, then the PIM core can make its writes permanent in memory and clear all of the signatures for next time. If there is an overlap, that means that a conflict may have occurred. So at that point, only the dirty lines in the processor that match in the PIM read set are flushed back to DRAM. The PIM core then invalidates all speculative cache lines and rolls back its program counter to the checkpointed value. At that point, the kernel starts executing again at the beginning. There is a small amount of hardware overhead that comes with this in 4 places. 1 bit per page of DRAM capacity, 1 bit per TLB entry, a 0.2% increase in the PIM core L1 size because of marking speculative data, a 1.6 increase in PIM core L1 size for the dirty mask, and in the worst case, 12 kilobytes for the signatures per PIM core. The authors do point out, though, that there is room for improvement here, and in future work, this overhead will probably be reduced. To evaluate lazy PIM, 2 kinds of workloads are used: graphs and databases. The graphs come from Ligra applications, PageRank, Radii, and connected components, with input data coming from real-world network datasets. And for the databases, a custom in-memory database is used with a transactional workload of 200,000 transactions and an analytical workload consisting of 256 analytical queries. The source code for these applications is annotated with the PIM macros to define where the PIM kernels will be and the PIM data. This is done with the help of a tool called O-Profile to select candidate PIM kernels that minimize cache misses, and then from those, the final kernels were selected by minimizing data sharing between the processor and the PIM cores. The evaluation is done with a modified version of the Gem5 simulator with the x86-64 architecture and the DRAM Sim2 to simulate the DRAM. The main processor is set to use 4 cores, 2 GHz, 64-bit Linux, 64 kilobytes level 1 cache per core, and 2 megabytes level 2 cache. There are 4 PIM cores, 2 GHz, 64 kilobytes per core, level 1 cache, and the main memory is HMC 2.0, 1 4 gigabyte cube, 16 volts per cube, 16 banks per volt. The first measurement taken was the normalized off-chip traffic, both as a function of each of the workload types and also as a function of the number of threads, using each of the 5 cache coherence methods discussed earlier: CPU only, fine-grained, coarse-grained, no cache, and lazy PIM. Lazy PIM significantly reduces the overall off-chip traffic up to 97.3% over no cache, and by 58% on average over coarse-grained, which was the best prior approach that we had. Lazy PIM also scales the best with higher thread count compared to the others. These next charts are similar, except they're measuring the speed up. Of course, the ideal PIM approach, which means that there's no penalty for cache coherence, perform the best in all cases. But lazy PIM performs very closely, and it outperforms all of the other approaches. In some cases, no cache and coarse-grained actually perform worse than CPU only on these workloads. The best prior approach we had was no cache, and lazy PIM outperforms it by 49% on average. Lazy PIM again did well in terms of scaling with thread count. On the PageRank application, lazy PIM came within 5% of ideal PIM, and did between 30 and 70% better than the other approaches on average. The difference in performance between lazy PIM and ideal PIM, although small, seems to come from the number of conflicts that are detected at the end of the PIM kernel execution. When there is a conflict, the kernel has to be started over again, or rolled back. Interestingly, the authors found that in all of the applications, a kernel never has to be rolled back more than once. The authors also point out that they believe they can improve the performance of lazy PIM by optimizing the commit process to reduce the rollback overhead. So, in summary, lazy PIM is a very efficient way of providing cache coherence between PIM cores and the main processor without significantly increasing the traffic on the main memory channel and increasing performance by roughly 50% over the next best method. To round out the presentation, I will now talk about some related work in the field that the paper covers. First is a little history of processing in memory. The earliest proposals actually date back to the 1970s, where it was suggested that computers could be built from many distributed, smaller, simpler logic units and many smaller distributed memory modules. Following that, a few notable examples over the years were Execube, TerraSys, iRAM, and computational RAM. And later, other architectures were proposed for use in DRAM, such as FlexRAM, DIVA, Smart Memories, and Active Pages, although many of these were too costly and did not solve enough problems to warrant mass adoption. Lately, there has been an increase in PIM proposals, probably due to the creation of 3D stacked memory. There is particular interest in the logic layer, and there are several proposals for adding computation. So far, these have mostly been aimed at special use cases like MapReduce, matrix multiplication, data reorganization, graph processing, databases, in-memory analytics, genome sequencing, data-intensive processing, consumer devices, and machine learning. Some more general purpose ideas include PIM-enabled instructions, GPGPUs, or single instruction multiple data, SIMD. There has also been work done on processing using memory. The distinction of processing using memory instead of processing in memory is that it is referring to exploiting the inherent properties of standard DRAM architecture without a logic layer to perform bulk operations on memory lines, such as copy, data initialization, bitwise logical operations, and simple arithmetic operations. While these techniques can certainly increase performance in special use cases, they are harder to generalize or adopt, and they still suffer from the shortcomings we discussed, such as address translation and cache coherence. There has also been some work done on processing in the DRAM module and memory controller. This would mean a change one or two organizational layers higher than the DRAM chips, so the chips would not need to be modified. Some examples of this kind of architecture are Chameleon, Gather-Scatter DRAM, and work by Hashemi et al. Even though they offer some benefits, they fail to take advantage of the high internal bandwidth in DRAM chips. For a PIM proposal to get adopted, one thing it needs is a good programming model. Lazy PIM, which is presented in this paper, is not the only one. There has also been work done by Sura et al. And Liu et al. To make it easier for programmers to adopt. And a PIM proposal also needs to make sense from a hardware point of view. Impika, presented in this paper, is not the only one. There is also work by Hassan et al. And Kim et al. That solve hardware-related problems in this area. Regarding cache coherence, other proposals have sidestepped the issue in order to avoid the increased overhead resulting from traditional fine-grained coherence. One way around it is to restrict PIM processing logic to execute on only non-cacheable data. Another approach is to use coarse-grained coherence or coarse-grained locks, which force CPUs to not touch any data that might be used by PIM, or to flush that data back to DRAM before the PIM kernel begins. This paper advocates for lazy PIM, which is the best of both worlds, as the PIM core handles coherence speculation and messaging is kept to a minimum. Whereas the in-mem-proc technique presented in this paper was an in-memory accelerator, there have also been CPU-based accelerators. One of interest is WIDX, which accelerates hash table lookup in a CPU in a modified RISC core. This is useful in database applications. It differs from in-mem-proc in that processing in memory has a different set of challenges to solve. WIDX does take advantage of the existing address translation hardware in a CPU, although it achieves parallelism only at the core level, whereas in-mem-proc is parallel at the PIM core level. On the wider subject of reducing the bottleneck of memory latency, many proposals have used prefetching to hide the latency. There are many ways to do prefetching, including software, hardware, or a combination, or in pre-execution. One drawback is that they depend on predictable traversal patterns, which cause them to become inefficient with unpredictable patterns. Another drawback is if they use CPU structures and are implemented in the memory controller, there will be much less efficient use of cache and the memory channel. There are a few other system-level challenges for PIM adoption. There needs to be a good programming model for programmers to interact with PIM processing logic. This is currently an open research topic. As seen with in-mem-proc and lazy PIM, there can be APIs exposed that provide fine-grained yet easy-to-use control over PIM. That gives the programmer the ability to realize serious gains in performance, but mistakes could make performance worse. It would be great if a compiler could decide the optimal places to use PIM code, which would make the programmer's job easier and maybe lessen mistakes. Another open research direction is data mapping. To maximize benefits, data that need to be accessed by a PIM kernel instance should be mapped to the same memory stack. So it's important to consider different data mapping mechanisms to intelligently map data. It is also beneficial to provide low-cost and low-overhead data migration mechanisms to facilitate easier PIM execution in case the data mapping needs to be adapted to execution and access patterns at runtime. There are some things to consider with PIM runtime scheduling, such as deciding when to enable PIM execution, what to execute near data, how to map data to multiple hybrid memory modules, and how to effectively share and partition PIM accelerators at runtime across multiple threads. Using locality prediction or dynamic code identification may be options. Future research will ask, what are simple mechanisms to enable, disable, and throttle PIM execution? Should it be affected by access patterns? Which parts of the application code should be executed on PIM, and what are the best ways to identify it? What are the best scheduling mechanisms to share PIM accelerators between multiple cores? Two kinds of granularity should also be investigated. The granularity of execution, i.e., how big should the code blocks be, and granularity of synchronization, i.e., how often should the PIM and CPU cores synchronize. Open questions here include, are there minimum and maximum lengths of code that are optimal to run on PIM, and should it be enforced? Should PIM allow synchronization with CPU cores, such as locks, and if so, how? To help with adoption, there need to be good ways to evaluate the benefits of PIM using real-world memory-intensive applications and simulation so that developers can fine-tune their PIM-enabled code. A set of benchmark PIM-enabled applications would help demonstrate the benefits. These could include data parallel applications, neural networks, machine learning, graph processing, data analytics, search filtering, mobile workloads, bioinformatics, Hadoop Spark programs, and in-memory data stores. And finally, it is worth considering newly emerging memory technologies besides DRAM. We may be reaching the limit of what we can do to work around its latency and scaling issues. There are a few examples of non-volatile memory that may end up replacing DRAM, such as phase change memory, spin transfer torque magnetic RAM, metal oxide resistive RAM, and memristors. PIM could take advantage of these technologies' huge capacity and very high internal bandwidth. PIM may also be useful in a single-level store where multiple memory types are presented to the system as a single monolithic memory. So, in conclusion, to wrap up the overview of in-memory processing, we are trying to find ways to work around the latency issues of DRAM and how it is accessed by a processor through a relatively narrow bandwidth channel. Modern applications are working on larger and larger datasets, which makes it worse. By moving some parts of computation away from the CPU and towards the memory, we can help alleviate the problem. This can be done in ways ranging from simple tricks like using DRAM's sense amplifiers, all the way up to logic layers in the 3D DRAM executing intelligently scheduled PIM kernels using parallelized algorithms and achieving coherence with the system cache. As the numerous open research topics are explored to make PIM even better, we can look to previous works to be reminded that adoption of these new protocols will only come when their performance benefits can be demonstrated and realized with minimal friction. Thanks for watching.